The second part of this unit is going to deal with linearization. So let's talk for a second about why having a linear graph is so useful. So let's suppose we're in the lab. We've taken some data on two different variables and we want to see how they relate to each other. If we end up with a graph that's linear, okay, showing the relationship between those two variables, there's a lot of information we can get from that graph. Number one, we can find the slope, and that slope is going to tell us how that y variable changes with respect to x. Okay, if we think about a position versus time graph, all right, it's going to tell us how the position changes with respect to the time, which is also known as the velocity. That's a useful piece of information. The y-intercept is another useful piece of information that tells us what the value of y is when the value of x is 0. Going back to position versus time, all right, it tells us our position when time is 0. In other words, it tells us our initial position. That's another useful piece of information. And lastly, and we did this some for the pullback car lab, we can calculate the r-squared value, which lets us know how well that line matches our data points. Now, we could do this for nonlinear graphs as well, but this is something that we can also do for linear graphs. So there's a lot of information we can get. So the question is, what happens when we have a nonlinear graph? If we have a nonlinear graph, we can't find that slope to see how the one variable changes with respect to the other. The other thing that's going to happen is it's very easy for us as humans to tell if a graph is linear or not. If it's nonlinear, it's a little bit harder to tell what the relationship is. For example, if you have a graph that looks like this, that might look like y equals x squared, or something times y equals x squared, but it also could easily be y equals x to the fourth. All right, it's not always clear that that is definitely y equals x squared. All right, so we're going to learn this technique here called linearization that's going to help us with this problem. So linearization is a technique that's going to allow us to take a nonlinear graph and turn it into a linear graph. Okay, so let's say we took some data on two variables, and what ended up happening was the relationship between those two was quadratic. Okay, so the one variable on the y-axis was equal to some constant times the x-axis squared. So that's not going to form a line, that's going to form a curve, something like that. Okay, so how can we take that exact same data? Okay, we can't change the data, that's not okay, but how can we take this exact same data and create a graph that is linear? All right, and the answer is, instead of graphing y versus x, we're going to graph y versus x squared. Okay, so I know that might sound a little bit weird. Okay, we're actually changing in some ways, applying some function to one of the variables that we've graphed. But what it does is it makes it linear, and it allows us to do some analysis on it that we couldn't do otherwise. Okay, so the reason why it's working here, right, is that x is no longer our variable. X squared is our variable. And so now this graph is in the form y equals mx plus b. We have some constant m times the thing that's on our x-axis, which in this case is now x squared. And so that graph, all right, will end up being a line. So let's take a look at this in practice. So here we have a graph with some data taken on oranges and apples. Okay, doesn't really matter what the experiment is here, but we end up with a graph. All right, we go ahead, we graph it, and we end up with a graph that clearly is quadratic. Okay, it looks quadratic. All right, and we even see from our equation for the line of our best fit, obviously we're using Excel here, but we see from that equation that it is quadratic. It's raised to a power of about 2. Not exactly 2, but about 2. Okay, so what we're going to do is we're going to graph apples squared on the x-axis. Right, so rather than apples, we're going to change that to be apples squared, and we're going to see what that does to our graph. So when we do make that change, all right, we clearly see that this has become a linear graph now. Okay, we see that just from looking at it, the data clearly matches the line of best fit very well. We see our r-squared value is extremely high, 0.99994. Okay, so this is a very, very good fit. And so we've taken now a quadratic graph, a curved graph, and turned it into a linear graph by simply changing what we put on the x-axis. Okay, rather than apples, we're graphing apples squared. So what does it mean? Okay, what does it mean here when we do that? Well, we can get a few really important pieces of information. The first is we've just verified that the number of oranges is proportional to the square of the number of apples. Okay, the fact that making that change and putting apples squared on the x-axis leads to a linear graph means that we've proven the relationship between apples and oranges. We've proven that apples squared is proportional to the number of oranges. All right, so that's the first really, really important piece of information. We now know what that mathematical relationship is between the two variables. The second is, all right, with that slope, we can say that the slope is about 2, so the number of oranges increases at a rate of 2 oranges per apple squared. Okay, so that's a useful piece of information that we can get from our graph. Lastly, all right, we can get our y-intercept, and that has some meaning as well. The y-intercept in this case is basically 0. Okay, if you look at that graph, it was 0.0923, which is so small, so much smaller than the actual data points that we had, that we can call it 0. So we can say that when there are no apples, there are no oranges. All right, and that's what that meaning of that y-intercept is. When there's none of x, how much of y is there? So we've now seen an example, all right, and let's talk for a second about, in general, how we're going to linearize graphs. The first thing we want to do is we want to determine what mathematical relationship exists between the variables, all right? There's going to be a few things you can look at. In some cases, we'll be trying to prove a mathematical relationship that we already know, and then it's pretty easy to figure out which should be graphed on the x and which should be graphed on the y. In other cases, we might just be looking at what the graph looks like and determining it from that. But that's the first thing we want to do, is try and determine the mathematical relationship between the two variables. The second is to isolate the dependent or y variable. So we want to get y all by itself on the one side. Okay, and that's going to help us to figure out what we need to graph on the x-axis to make it linear. And then we're going to change one of the axes to match that relationship. I typically tend to just change the x, although it's not incorrect to also change the y-axis in some circumstances. But I usually, my first thought is usually to try and change the x. All right, so we talked about how sometimes you're going to get that relationship from looking at the graph itself. So let's talk about a few different graphs and what they look like and what the mathematical relationship they show is. There are about 4 that you should recognize right off the bat. There are others, obviously, that exist in the world, but there's 4 pretty common ones that you should be familiar with. So the first is just a linear relationship. Okay, that's the easiest one to recognize. Its equation is y equals mx plus b, where m's the slope and b is the y-intercept. All right, so that's the first basic graph that you should recognize. The second is a square root graph. Okay, it has the look where it's concave down, okay, but increasing. There are other graphs that look like that. Logarithmic graphs also have a similar look to them, but we're just going to stick with square root graphs for now. In that case, that graph is the equation is going to be y equals k, some constant, times the square root of x. There could be a y-intercept as well, but we'll just stick with a basic form where it's y equals k times the square root of x. The next one is a quadratic graph. We looked at an example of that with the apples and the oranges a few minutes ago. Okay, and that one has a basic form y equals k times x squared. All right, it looks like really just half of a parabola, basically. We're just simply missing the other half that would be over here, but concave up and increasing. All right, once again, there could be a y-intercept here, but this is the basic form for one that goes through the origin. And the last type we have is one that looks like this. Okay, we see that as x increases, our y values decrease. That makes it an inverse function, which has the basic form y is equal to k, some constant, times 1 over x. Okay, so there we have the basics of the types of graphs that you should recognize. We'll do some practice with this in class. So the second part of this linearization business is verifying a known relationship. So there will be some times when we know what the relationship between two variables should be, and we want to verify or prove that that relationship is correct, okay, using a graph, using linearization. So what we're going to do here is we're going to rearrange that known equation, that known relationship between the two variables, predict what kind of graph it should give us a linear graph, and then graph it and see if it does. And if it does, all right, it supports that equation being the correct relationship between the variables, right? The other thing we can do with that is a lot of times if we know what the relationship is, we can also figure out what the meaning of the slope is and what the meaning of the y-intercept is. A lot of times those two numbers have some physical meaning. They represent something, and we can see how closely they match the values that they actually represent in real life. So before we work through a quick example here, keep in mind that the equation of any line is described by y equals mx plus b. So our goal basically when we're rearranging these equations and figuring out what we're going to graph is to get that y dependent variable by itself. Okay, whatever's on the y-axis, we want to isolate that first. Okay, and then we're going to be able to determine what to put on the x and what the meaning of our slope and y-intercept is going to be. Alright, so here's our example that we're going to work through. We're dropping a ball from some height, right, and we're going to vary the height that we drop the ball from while measuring the time that it's in the air. So, knowing our kinematics equation here, starting with delta x equals vit plus 1/2 at squared, our initial velocity, since we're dropping it, is going to be 0, right? That's going away, right? And so I'm just going to replace delta x with height, and we're left with this relationship. Height is equal to 1/2 times at squared. So thinking about our dependent and independent variables, okay, the thing that we physically control in this situation is the height. So that makes that our independent variable. That's the thing that we have control over. And the thing that we're measuring that we don't control directly is the time, right? We don't say we're going to make it fall for 1 second. We say we're going to drop it from a height of 1 meter. So 1 meter, the height, is our dependent. Time, which we're simply measuring and is affected by the height but is not something that we directly control, is our independent variable, or is our dependent variable. So the first thing we're going to do is we're going to rearrange this equation to try and solve for our dependent variable, to try and isolate our dependent variable. And so when we do that, we get time, or get that t squared term by itself. Okay, so we divide both sides by 1/2 a, which gives us t squared equals h over 1/2 a. Fixing that double fraction, we're left with t squared equals 2h over a. So that's the first thing we want to do. We've now isolated our dependent variable here, which is that t squared. The next thing I'm going to do is I'm going to pull out any constants over on the right side of my equation. So in this case, 2 obviously is a constant, it's just a number, and my acceleration, which will be the acceleration due to gravity, is also a constant. So that 2 over a is a constant, and so we're left now with our independent variable, or our dependent variable, equals some constant times our independent variable. And that's the basic form we want to get this in. Now there could be a y-intercept here or an extra number here. We don't have that in this case, but if you had that, that would also be okay. But you want to get dependent variable by itself on one side, and then pull out any constants from your independent variable to isolate that. Once we have this in that form, we're simply going to compare it to the equation that we know for a line. So we have the equation t squared equals 2 over a times h, all right? And I'm going to compare that to y equals mx plus b. So the first thing that we notice matches up is the t squared and the y match up, and that means that the y-axis should be t squared. Okay, so that's the first piece of information we can get. The second is that x matches up with h, our height, which means that the x-axis, we're going to graph our height, h. All right. Third thing, the slope, All right, we actually know what the slope of this graph should be. The slope should be 2 over a, all right, because that's what matches up with our slope there. Once we have it in this form, right, we just simply match it to y equals mx plus b. So we know our slope should be 2 over a. Lastly, our y-intercept, there's nothing there, so our y-intercept should be 0. So if we were to graph this function, we would put t squared on our y-axis, we would put height on our x, and we should get a line that has a slope of about 2 over a. Obviously, there'll be some error that will lead that to be not exact, and a y-intercept of about 0. Okay, that's what we should get if we were to take this data and graph it, and that would help to prove this relationship that we started with, or to that actual. So just a few tips here for doing this, okay? Some things that we just saw. We first identified the two variables, the independent and the dependent, and rearranged to solve for the dependent. We pulled out any constants that are multiplied by the independent variable, and then we just matched it up to y equals mx plus b. All right, so we'll work through a few of these practice problems in class as well, but you have the basic idea now.